Hello and welcome to the video key for the Unit 1 take-home test. Okay, let's get going. Just like we always do with our take-home tests, we've got I do, we do, and you do problems. Anything that's already done in RenPed, you are fine to check your work and change your answers. Anything you see highlighted in blue is something I'm going to work on the video tutorial. Anything that's highlighted in green, I am not going to do on the video tutorial. That's for you to practice at home. Okay, so this first section, this fill-in-the-blank notes, you can take a look at what I already have to check your answer. One thing I want to point out is when they're talking about opposite spins, they mean up arrow, down arrow. And I put in some little hints about the periodic trends as well. Go ahead and pause it if you need more time on that. Down here for electron configuration. Electron configuration, there's no noble gas shortcut. That's the full way. So I gave you this one to look at, and let's do iron together. So for electron configuration, we let you use this periodic table on your exam. So if we're looking for iron, I always recommend that, that my students get two little pieces of paper for this. Okay, this is Miss Holm, by the way. Welcome. So you're going to put one piece of paper where you're going. So we're going to iron for our first example, and we're starting here. So we're going to account for where iron's 26 electrons are arranged. That's what electron configuration is. So iron's first two electrons are here, 1 and 2, and that is 1s2. We'll say 1s2. Okay. So after electrons 1 and 2, we go to electrons 3 and 4, and they are both in 2s. So we'd say there are 2 electrons in 2s. After electron 4, we can't come down here to 11. We go all the way across to electrons 5, 6, 7, 8, 9, and 10. So those 6 right here are in 2p, 2p6. So now I've got my first 10 electrons right there. So after electron 10, we come down to electron 11. 11 and 12, those two are in 3s. So we say 3s2. After electron 12, we have to come over to 13 through 18. And those 6 are in 3p, so 3p6. Whoops, sorry. After electron 18, we go 19, 20 are in 4s, so 4s, 2 electrons in there. And then after electron 20, we go to 21, and those are in 3d, but we stop at 26. So I'm only going to have 6 electrons in 3d. So I'd say 3d6. All right. Go ahead and do oxygen that same way, and you can check your answer for calcium. The noble gas notation is when you can do the shortcut. So make sure you're starting at a noble gas, which I'm going to outline here. We've got our family 18 as noble gases. Okay, so it's a shortcut from any of these, or from helium. Remember, on our other periodic tables, helium is usually right here. So helium is a noble gas, even though it belongs in the S block here. So I did nitrogen. You can kind of check the answer for nitrogen. Again, I'm going to take my two pieces of paper, and I'm going to say potassium sulfur, the blue one we're doing together. So we're going to talk about sulfur's first 16 electrons, but instead of going 1s, 2s, 2p, like we do for the full configuration, noble gas shortcut, we're going to start from the last noble gas that we've passed. So for sulfur, 16 electrons, we haven't talked about electron 18 yet, but we have talked about electron 10. So we can say, all right, guys, starting at neon, because that represents the first 10 electrons. After the 10th electron, we go to electron 11 and 12. All right, and those two are in 3s. Excuse me. Yeah, 3s, I'm right. So those two are in 3s, 3s2. After electron 12, we go 13, 14, 15, 16. Those 4 are in 3p. So 3p4, and that's supposed to be a 2. It looks like a 1. 2. Okay. So there's our shortcut. So if we go these 10 electrons plus 2 plus 4, that's a total of 16 electrons. That's how I can check and make sure that it is sulfur. All right, do that for potassium on your own. So that's the full configuration and the noble gas shortcut. Orbital notation then is the arrows. So it's just the same 1s2, but I show them as up-down arrows. So take a look at how we did this one. Take a look at your homework if you need, but that's how we do lithium as well. Go ahead and do that. Looking down at these ones then, noble gas notation for nickel I did. Noble gas notation for yttrium. So I always tell my students, on a multiple choice test, you have to take out the garbage. So garbage for S, yttrium is right here, number 39. So if I'm going to do the noble gas shortcuts, yttrium hasn't gotten to 54 xenon yet, so noble gas shortcut should be from krypton. So I'm going to look here, we haven't gotten to xenon yet. So that's garbage. I took out the garbage. Then I'm going to look at where I go after, let me get that on there, where I go after krypton. So after electron 36, I have to go to electrons 37 and 38. And those are in, whoa, there it is, that scared me. Those are in 5s. So I have 5s2 next. And then after 5s2 for yttrium, I go to 3d, 3d1. You know what? The right answer is not even there. Look at that mistake. Okay, so we should say 3d1 there and there. So there's the problem. 4d1 next. Okay, to 4d1. So this would be the right answer if it said 4d1. There we go. We're going to have you circle A. For number 7, last valence electron of vanadium. That's just asking for vanadium's address. Okay, vanadium is number 23. It's right here. So its 23rd electron is in 3d3, right there. So vanadium's address is in 3d3. Correct electron configuration for chlorine. So the first thing we're going to do is find chlorine's address. Chlorine lives in 3p5. So my answer has to end in 3p5, not 3p1. There's 3p5, not 3p6, not 4p5. So now that I've taken out the garbage, I can come back and say B. All right, let's look at page 2. All right, sorry, I'm making my papers in order. All right, the current model of the atom is known as the, look it up in your notes, but I'll give you hints. 2 words. First word starts with Q. Second word starts with M. So spell them out if you need to look it up in your notes. I'm going to have you all do 11 on your own, but we're going to do it the same way we do 12. Okay? So they gave you the configuration, 1s2, 2s2, 2p2. So I'm going to come and find who lives in 2p2. That's carbon. I'm going to say it belongs to carbon. Right? And then they want to know what group and period carbon lives in. And that information is not on this periodic table. You're going to have to turn it over. All right? Carbon lives in group. Remember, groups are up and down. And periods are side to side. So carbon is right here in group 14. You could also say 4A. And carbon is in period 2. If you switch that, if you said group 2 and period 14, you would have that wrong, people. There are only 7 periods on the periodic table. Just be careful with that. Okay, looking at number 15, if you are watching, you get extra credit for doing this. Okay, right here, it says, which of the following breaks Aufbau's principle? And that's when students go, oh my gosh, I don't know, and they just guess the answer. So for us, we're going to make a uh-oh face. Oh no. I don't know if that's a surprised face. Maybe we'll go like eyebrows. That's a terrible surprised face. But say, oh no. I don't know this one. Okay, extra credit for that. We're not going to freak out when we see that. We're not going to go look up Aufbau's principle. It's just saying, of these 4 choices, one of them is wrong. So according to the rules we learned in class, which one of these is wrong? Now that's a lot of numbers, it's a lot of letters, there's little numbers. I like to just kind of compare and contrast. So first, they all say 1s2. So no one's breaking any rules there. Then they all say 2s2. So that's fine. Then we have 2p6, 2p6, ooh, 2p2. That's different. Then they all say 3s2, and then the ends are all different, and that's fine because they're just different elements. The ends don't have to match. But that guy in the middle, that's breaking Aufbau's principle. Aufbau's principle says electrons are lazy, like teenagers and tired teachers. They want to do low energy first. So we'd never put an electron into 3s2 if there was still room in 2p. So there we go. We didn't panic. We found the answer. That's not a very good surprised emoji. So hopefully yours is better. Sorry. Go ahead and try the same thing for 16 now. Okay, you can check those answers. You're going to do 19 and 20 on your own. For 21, this question 21 is the same as this question from Unit 1. What group, remember groups are up and down, what group on the periodic table does this valence orbital notation represent? So that's the same thing as saying, what group on this periodic table does this Lewis dot structure represent? So last unit we would have said 1, 2, 3 valence electrons, so it's group 13 or 3A. Now we're going to count 1, 2, 3 valence electrons, so it's group 13 or 3A. Okay. Alrighty, now we're getting into periodic trends, so you will get this periodic table on your exam, a blank copy. You're not going to get your own copy, but you'll get to use one that looks just like this. So I like to tell my students, my homies, to use 4 little pieces of paper on this. And let me get some. I should have been more prepared. Sorry, guys. But for this one, number 24, which one has the highest ionization energy? So I'm going to look, for ionization energy, that's following these arrows. So right here is pointing towards the big one. So if we're going to look at ionization energy, we're comparing sodium, sorry, I'm going to have to keep moving this a little bit, chlorine, comparing silicon, and we're comparing magnesium. Okay. So instead of kind of putting my fingers and trying to read over it, I've got my 4 pieces of paper and I can say which one's the highest ionization energy, or the largest. So I know that the big part of the arrow points towards the biggest. So as I move this way across a period, it gets bigger, which means this is the furthest over. That's going to be my biggest ionization energy, which is high chlorine. All right, so I'm going to go ahead and say chlorine is the biggest ionization energy. Okay, that's what you're doing for 23 and for 25, except for 23 you're doing it with atomic radius. So we're comparing using these arrows, where this one's the biggest for atomic radius. All right, go ahead and turn over to page 3. All right, here on page 3, we're going to have you do electronegativity. Oops, excuse me, let me get on camera. We're going to have you do electronegativity on your own, and you can check your answer for 28 and for 29. You're going to do 31 the same way you did 29, and that was nitrogen is in group 15, or 5A, so it has 5 valence electrons. So I said mom and dad share the first bedroom, and then 3, 4, 5, they each get their own bedroom first. Okay, an atom of fluorine more strongly attracts electrons in a bond compared to an atom of calcium. This is because fluorine has a higher blank than calcium. All right, so we're going to take a look and we can compare fluorine and calcium. Now fluorine's right here on the periodic table. I'm going to put a piece of paper there, and calcium's over here. So we can check atomic radius. Does fluorine have a bigger atomic radius? Okay. No, calcium would have a bigger atomic radius. So I can take that out as garbage. Does fluorine have higher ionization energy? Yes, it does. It also has higher electronegativity. And does it have higher resonance? We haven't used that word yet, which means that's not your answer. If you haven't recognized it before, don't pick it. So by taking out the garbage, we're down to ionization energy and electronegativity. Okay, attracting electrons in a bond. That's someone else's electrons. So that's attracting extra electrons. And E for extra electrons is E for electronegativity. So there would be our answer. Ionization energy measures the attraction to an atom's electrons. So it would be its own electrons. If it was IE, it would be its own electrons. Looking at 33, wow, I can read. Compared to the atomic radius of krypton, the atomic radius of neon is blank. This is primarily a result of neon atom having blank. Okay, so we're comparing atomic radius for neon, right here, and krypton, right here. My atomic radius arrow says it gets bigger as you move down, which means neon is smaller than krypton. So if we look, it says the radius of neon is smaller than krypton. So it is smaller, it's not larger, there's garbage. It's not larger, it is smaller. So I'm down, just by taking out the garbage, I'm down to A and D. Because neon has more protons, Neon has 10 protons. Krypton has 36. So neon definitely doesn't have more protons because it has fewer energy levels. Yeah, neon's here in period 2, so it would only have 1, 2 energy levels, versus krypton in period 4 would have 3, 4, I'm out of there, right? Energy levels. So that's a bigger radius. It's a bigger circle. So you'd say, yeah, there's my answer, letter B. All right. That's the same way I did 34. I'm going to let y'all do your own here by using those words. Check your notes if you need to. Let's go down to balancing nuclear reactions together. All right. Now, I really wish we had more room, and I apologize for that. But looking at number 39, what we have is 138. If we just look at the top numbers first, 138 equals something plus 0. So I'm going to rewrite that as algebra over here. 138 equals something plus 0. So what plus 0 is 138? Well, it's still 138. So that's going to be my top answer, 138. For the bottom answer, on 39, I have 53 equals something plus -1. All right. So something, take away 1, is 53, which means it should be 54. All right. So 54 on the bottom. And if you want to put that in your calculator to check it, 54 plus -1 equals 53. All right. So that's how we know we're doing that right. And then for the symbol, we have to find number 54 on the periodic table. All right. And 54 is right here, xenon. So the bottom symbol should match right there, Xe, xenon. So this is beta decay. One of the neutrons turned into a proton by ejecting a beta particle. Looking at this one, then, I'm going to get a different color, number 40. Number 40 says on top, and I'm going to write it down here, blank equals 11 plus 0. That's what this says. Something equals 11 plus 0 on top. Well, 11 equals 11 plus 0. So this top number is going to be 11. On the bottom, it says blank equals 6 plus -1. Right? Now, instead of saying -1, you can say take away 1. But 6 plus -1 equals 5. This one should be 5, and number 5 is not number 7, nitrogen. 5 equals 6, take away 1. That's true. 7 doesn't equal 6, take away 1. So be careful on that one. All right? All right. Page 4 it is. Let's move on. All right. Some more balancing up here, but now it's looking a little bit different. Where it says, what's the missing symbol X represent? So we're still doing the same thing. I'm going to write it up here. That 154 equals something on top. We don't know what those numbers are. Plus 4. So what number plus 4 equals 154? So for algebra, if this is X, we'd subtract 4 from both sides. That would cancel out. So we'd say X equals 150. So I can start by taking out the garbage. The top number is not 154. It is 150. It is 150. And it's not 158. So I don't just want to pick this one, because this one's also 150. We have to keep going. So if we're looking at the bottom numbers, we have 61 equals something plus 2. So we subtract 2 from both sides. 59 equals X. Then we look down here and we say that's number 59, and oh shoot, that's also number 59. So then we have to make sure our symbol matches. If I lost 2 protons, I'm not PM anymore. Okay? On the periodic table, number 59, whoops, is on this side, excuse me, PR, promethium. PR, so we're going to say there's my answer, because that's not the right symbol. For this one, what's the missing particle? This is a little bit trickier, not too bad. So what we're going to do for this one is still solve for the numbers here. Okay, so we have 9 equals 9 plus, this top number has to be 0. And 3 equals 4. The only way that 3 can become 4 is if I take 1 away from it, so -1. Then this is where it's going to be helpful to know on your test copy of the periodic table on the back. there's a nuclear section. Okay, so you're going to get this on the exam, and it tells you 0, -1 e is a beta particle. So you say the missing particle is the beta particle. All right, okay? All right. Go ahead and draw this one. You can check your answer. All right. So there's that. We're going to look at number 51 is mean. Because 51 is the same thing as this, but I don't give it to you at all. You have to write it. Okay? So carbon 14. That's carbon that has a mass of 14, and carbon is atomic number 6. So we're starting with this. There's carbon 14 in isotopic notation. It is going to undergo a reaction, and they're asking, what is left? Well, shoot. Okay? We tell you that it's alpha decay, which means one of these particles has to be the alpha particle, 4,2 He. All right. Now we've written a problem that we're used to looking at. So 14 equals 4 plus, that would have to be 10. 6 equals 2 plus, that would have to be 4. Number 4 on the periodic table is beryllium, Be. That would be Be, which means, ding, 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 got them right there. For this one, this is Unit 1. We had questions just like this on the Unit 1 test, where it's mass minus atomic equals neutrons. So let's take a look at what we can say about this. For sure, you guys should know that that bottom number is the atomic number. So that is protons, okay? So 94 protons and 94 protons. All right, there's no garbage to take out. But we also know that protons equal electrons. So this should also be 94 electrons, not 239 electrons, 94 electrons, not 145. Okay? So I already know my answer is not D and it is not C. But now I need to worry about this. Okay? 239, that's the mass. That's not the neutrons. The mass would be the big number minus the little number. So we would say 239 minus 94 equals 145. So there, B is my answer. Okay, that's what we talk about when we say taking out the garbage. All right. I'm going to have y'all use your notes to do this because you'll learn more by looking it up. There's two things that they have in common. So I put changes the nucleus and releases a large amount of energy. And then 3 of these answers belong to fission, and 2 of the ones that are left belong to fusion. So check that in your notes. That'll be page, I think it's page 12 in your notes. All righty, one more page. We're doing great. If you are still watching, I've got some more extra credit for you. Okay? If you write man there plus 2, then you're going to go ahead and get 2 more points extra credit. And this is just my work for how I did number 54, so you can check that. All right, 55 is a lot like the one we just did, carbon 14. It says if silicon-29 undergoes beta decay, what will it become? So I wrote silicon-29 in isotopic notation, where it's silicon with a mass of 29, and silicon has 14 protons, so I put 14 on the bottom. And it's going to undergo beta decay, so I'm going to look at the back of my periodic table, and it's going to tell me that, a beta particle is 0, -1 E. Right? So when we go 29 equals 0 plus, that would have to be 29. So yes, it is 29, 29, not 25, 29. All right, that got me down to 3 possible. 14 equals -1 plus something. All right, so I've got 14 equals -1 plus x. So I'm going to say minus -1 on both sides, minus -1, right? And we should know this from math, but people keep missing it. 14 minus -1 equals 15, right? Because subtracting a negative is the same thing as adding a positive. So it is 15, not 14. It is 15. Oof, I hope we didn't go too fast. Because 15 protons isn't silicon anymore. We said 14 protons is silicon. 15 protons is now phosphorus. So it's not silicon, it is phosphorus, so there is my right answer. A is almost right, which is wrong, but D is our right answer. Just a few more problems to talk about. Okay, you're going to need this graph. This is how I graphed the point for 56. For 57, we're going to say an isotope of cesium-108 is likely to have. All right? So I did mass minus atomic equals neutrons. Right? So first thing I can say is it will not have 55 neutrons. It's going to have 53 neutrons, not 55, 53. So I already know that A and B are wrong. Then my next choices are between is it stable or radioactive. So I'm going to graph 55 protons, because it says 55 right there. 55 protons right about in the middle here, versus 53 neutrons. 53 neutrons is right about there. So if we do that, that is not in the dark stable region. So I would say it's not stable. It's going to be a radioactive isotope. So my right answer should be D. Okay, that's the same way you're going to do 58, so try that one on your own. Then let's look at this one. The element tellurium has 52 protons. Could stable isotopes of tellurium exist? So we're going to look at 52, which is just above 50. So we're going to be right about here, looking in this area. Is there anywhere possible for it to be dark gray, stable? Yeah, that's a possibility. So that's why I crossed D out. It's only going to be too big once you start having this many protons. So once we're looking at like 90 protons, that's when we get too big to be stable. So these ones all say yes. How do I know which one to pick now? It says yes, it could be stable with about 52 neutrons. Okay, 52 and 52 is going to be right about here where that last dot was, and that's not stable. So that's not enough neutrons. 68 neutrons right about here. Ooh, that winds up in the stable region, so that looks pretty good. With 80 neutrons, that's going to be up here, and that looks not stable. So it can't be stable with 80. So now that I've taken out the garbage, I can come back and say C. Yeah, tellurium can be stable, but it needs about 68 neutrons. All right, same thing for number 60. More extra credit if you are still watching. Okay, we're skipping this. We took this off the test. So go ahead and do this. Harvey 8, page 6 of our review packet. So say, darn it, Harvey. And if you put that, go ahead and get 2 more extra credit points. This bottom part should have been completed in class. So if you did it with your teacher, great. If you didn't with your teacher, you'll have to check with them. Okay? Well then, hope you guys do great on that test.